Okay, so rotational energy is really a topic that's came up already during our energy unit. Now we're just going to fine tune our understanding of it and learn a couple quick tips to just make sure that if rotational kinetic energy comes up on the AP exam, you can just make sure that you get the questions right. But it is a pretty simple idea. So let's start with this example problem that I have in front of you guys where I have four different objects that are going down a slope. Three of them are dealing with, or two of them are dealing with friction. Two of them have no friction. Then I have some different shapes that are going down these slopes. So the question here is which one gets to the bottom first? Maybe let's see if we can figure out the correct ranking. So let's assume that they're all the exact same mass. They're all on the exact same slope. They're all basically everything's the same about them except what's stated as being different, which is their shapes and whether we're dealing with friction or not. So when we're trying to figure out who gets to the bottom of the slope, a lot of the time, something that students pick up very early on, especially if it tends to be if this is an FRQ, is they pick up on right here where it says there's no friction. And they think to themselves, well, if there's no friction, then it's going to get to the bottom first because there's nothing slowing it down. And that's excellent. That should go through your mind. That's a very good point. That friction is by definition a force that's going to be opposing motion. So if I draw a free body diagram for just one of these, I guess I'll do it for the one that has one of the ones that has friction. If it was no friction, I'd have force of gravity and normal force. And you can see that force of gravity is going to pull it down the slope. But the minute that I add friction in, you can see that there is a force that is opposing the direction of motion. In fact, I should add it. Let me redraw it real quick. The force of friction actually exists here along the base. But you can see that it's going the opposite direction of the acceleration down the slope. So that would slow it down. And there's nothing wrong with bringing up the idea of friction when you're answering these questions. However, there is another piece in here, and if you just stop after talking about friction, then you're going to miss some of the points if this is an FRQ. So the piece that you'd be missing is talking about the rotational energy, which is actually coming from the force of friction. So as we're going down this slope, let's think about this as an energy problem. Each one of these is starting with gravitational potential energy, but then when they end, they're going to end with at the very bottom of the slope. They're going to have some translational kinetic energy and possibly some rotational kinetic energy. Since energy is conserved in this system, we would expect that the energy at the beginning and the energy at the end would be exactly the same. So anything that increases the amount of rotational kinetic energy would decrease the amount of translational kinetic energy. So that's my first big tip, is that more rotational kinetic energy means less translational kinetic energy and therefore less velocity at the bottom. So based on that, we can say that B and D, since they're not going to, well, we can say that B will end up going the fastest at the bottom. But actually, let's talk about D real fast. If there's no friction, then the forces acting on the ring is going to be the force of gravity, mg, and the normal force, n. Notice that there's no force that's going to be causing a rotation here. The normal force is not creating a torque because it's acting at a right angle, or it's going right through the center of mass. And the force of gravity originates at the center of mass. So neither one of these is going to create any kind of a rotation. So actually, E and D will both end up going the same speed at the bottom. So VB is going to be equal to VD. So now that we've accounted for those two, let's talk about oh shoot, not A and D, B and D. So let's talk now about A and C, because we have this ring and we have this disk. So going back to the equation for rotational kinetic energy, Kr equals 1/2 I omega squared. We're going to look at these two different shapes and figure out which one of these ends up with more rotational energy at the very bottom. So looking at it real quick, notice that we have this term here, which is the rotational inertia. So let's talk about the rotational inertia of a ring versus a disk. A ring has the rotational energy of mr squared. So that's a ring. And for a disk, it is 1/2 mr squared. So just comparing these two objects then, if we're looking at the disk, the rotational inertia of a disk is smaller. Therefore, it would have more translational kinetic energy because less of the energy is going into the rotational kinetic energy. So based on that, the disk ends up going faster at the end, and then the ring will actually be the one that gets to the bottom the slowest. And that matches a lot of what we talked about last week, where we said the more rotational inertia an object has, the more it's going to resist acceleration. So since A has more rotational inertia than C is, it's going to resist the acceleration more and therefore be going less fast at the bottom than C is. Okay, so that's probably the biggest idea, is just looking at how rotational inertia affects the rotational kinetic energy. And so for this, I just want to point out you need to pay attention or pay special attention to rotational inertia. Rotational. If there is a question talking about different shapes going down a slope, whatever it is going to really come down to rotational, which one has the greatest rotational inertia, and that will be the slowest. It'll take the longest to get the bottom, least acceleration, all those values. The last thing that I'm going to put into this video real quick is if we are dealing with these two quantities, kt and kr, we're dealing with 1/2 mv squared plus 1/2 I omega squared. That's a lot of different variables that we're going to have to talk about. And if it comes time to solve the problem, we're going to have to somehow find ways to put some of these variables in terms of the other. So the last tip that I have, if we have something that does have friction, and the friction is enough that it doesn't slip at all, so if there's no slip, but only if there's no slip, then we can say that the velocity at the bottom is equal to r times omega. That lets us do a lot of substitutions right here, because we can start plugging in v over r for omega, and you'll see that in class and in a later video. But those are the 3 big tips for rotational energy. So I hope that all helps. Thanks. Bye.